Okay, so before we continue with section 2.5, which talks about transformations, for example, what I would say to all my students when we talk about transformation is this. Can I live in algebra and pre-calculus and calculus without transformations? I can. Why are they so important? It's because once I understand, or once you understand how transformations work, by simply looking at a function, not graphing it, not doing anything to it, you will be able to picture its graph in your head. So this is a very powerful skill to have. Understanding or knowing transformations, it's a powerful skill to have. Like factoring. Can you live without factoring? Of course. You can always use a quadratic formula if that's the case, right? But it's a very powerful skill to have. Okay. Before I even mention what they are, I have to review the basic functions with you. And we are going to add a lot more functions to this list that I'm going to present right now throughout the semester. First, a linear function. Can anyone remind us or give us the simplest possible linear function that you can think of? That's it. It's also called the identity function. It's not an important name. I just wanted you to know, but no one will test you on that. So let's look at this graph. And remember that, so y equals x, or f of x equals x, is the line that bisects the first and the third quadrants. It divides them in half. On this line, each and every point has the same x and the same y. So this point will be 3, 3. This point will be 2, 2. This point will be 1, 1. This point will be 0, 0. This point will be negative 3, negative 3. So it's a very important type of function. I'll come back to it in a minute after we finish the list and I say something about functions, and I'll come back. Okay, can anyone give us the simplest possible quadratic? Absolutely. Good. How do I graph a quadratic function? So what type of graph does it have? Of course, the line has a straight line. A linear function is a straight line. But what is the graph of a exactly, it's a parabola. Perfect. So this is the simplest possible quadratic function. Y equals x squared. Good. Next one. All these functions that I'm listing now come from the prerequisite courses. If you don't remember something, let me know. Okay, so the next one is the absolute value. Bless you. Yes, that is a v function. Awesome. Very good. So here's the graph. Can anyone give us the simplest possible absolute value function? We are looking at the... Very good. So f of x, the absolute value of x, is the simplest possible one. This does not have any transformations on it. It's the basic function. So here it is. So this is y equals the absolute value of x. I'll come back to all of them after I finish because I want to say something about each and every one of them. Can anyone give us the simplest possible square root function? Awesome. What is the domain of this function? Awesome. Or equal to. Very good. How do we graph it? Yes. Awesome. Here it is. From 0 going to the right. So y equals the square root of x. Perfect. Thank you. Number 5. Cube root. Very good. What is the domain of this function?
Looks like an S, right?
Yes. Yes.
Right, so-
You pictured it perfectly, so what would be its domain?
Yeah.
It's negative and positive.
Right, so what would be its domain? Awesome. Here's the graph of the cube root. Cube root is friendly. Square root is not. Very good. Six, cubic function. What is the simplest possible cubic function? F of x equals x to the third. Here's the graph of x cubed. And 7, rational. I only wrote here function, but please write function for everyone. Absolute value function, square root function, cube root function. Yes, can anyone give us a domain of the cubic function? Right, it's a polynomial function. All polynomial functions have domain or real numbers. Very good. Perfect. So now the rational function, please. The simplest possible rational function. Of course. Thank you. What is the domain of this function?
Everything but 0.
Awesome. Very good. So here's the graph. Okay. We're going to analyze transformations on these functions, but before that, I would like to talk about two types of functions. And then I'll come back to identify each and every one of those. These are two different functions, two types, with respect to symmetry. So this everything you see here that I'm going to write in this bottom half of the page, it's all about symmetry. Functions don't have to be symmetric. It's nice when they are. It's easier for us to graph. If I know that the function is symmetric with respect to the y-axis, it's easier to graph it. If I know that it's symmetric with respect to the origin, it's also easier to graph. So let's see when a function is even and when a function is odd. So let's take a look at, I'm going to copy a function and you'll tell me which one it is. Yes, very good. Y equals the absolute value of x. Perfect. And now I'm going to ask you the following question. So let's say this one is I pick some x value. And I draw a vertical line. I see it crosses the graph in a point. And then I want to read this value. What should this be if this is x?
Same.
No. Not necessarily. What I'm asking you, forget about the function that I wrote here. let's not really discuss any particular function, but if this is x and this is a function, what will this value be? Of course, that's all I want you to say. But you are right in this case for the absolute value. Good. So now I'm going on the other side, and exactly at negative x, I draw a vertical line. It crosses the graph in a point. And now I read what? Don't even look on the other side. I want you to be tempted to say anything about it. So if this is negative x, what should this be? Very good. Indeed. F of negative x. Absolutely. For any x value, I get f of x. For any negative x, I get f of negative x. Good. So obviously, what do you conclude by looking at the graph? What do you conclude about the relationship between f of x and f of negative x? Yes. So f of negative x equals f of x only when the function is even and its graph is symmetric with respect to? Of course. Very good. So even functions are symmetric. Of course, their graphs are symmetric with respect to, one more time. Very good. I lost track of my numbers. 5, 6, 7. Good. And the relationship must be this. If I cannot show this, then the function is not even. So let me give an example. Let's say f of x equals negative x to the fourth minus x squared. Is this function even? You should say, I have no clue. I have no idea. Let me calculate this. Okay. Negative x to the fourth minus negative x squared. How much is negative x to the fourth? How much is negative x to the fourth? Very good. With minus in front? Very good. How much is negative x squared? One more time. Negative x squared. Yes, with minus in front? Very good. Does this equal f of x?
Yes, it does.
It does. It's the same. It's the same. So then I will say the function is f is even. Awesome. Very good. Okay, so let's look at the other possibility. A function cannot be odd and even at the same time. However, there is one function that is odd and even at the same time, but nobody cares about this function. Here it is. This function. This is the only function that is odd and even at the same time. But as you see, nobody cares about it, right? Who cares about f of x equals 0, which is the horizontal line representing the x-axis? Right? So let's go back to odd. And you'll tell me which function I'm graphing. Yes, y equals x cubed. Good. So now, bear with me. Disregard the fact that it's x cubed. I just picture the function. So let's say I have my little x here. And what is this? Thank you. Of course, I'm going to have my negative x here. And what will this be? Not yet. This is negative x. What will this be? Of course. Now I'm going to ask you, what is the relationship between f of negative x and f of x? They can be the same. They are the same here. But what is the relationship now?
Negative to each other.
So they are opposites of each other, right? So then I will say that f of negative x must equal not f of x, but
Negative f of x.
that's it. And then the function will be symmetric with respect to,
X-axis.
there is no function symmetric with respect to the x-axis. If the function is symmetric with respect to the x-axis, is it a function or not? No. So an equation may be symmetric with respect, thank you for bringing that up, however. An equation can be symmetric with respect to the x-axis, but it's not a function. By the vertical line test, it's not a function. But it exists. Awesome. So what do we conclude then? Then odd functions are symmetric with respect to let me give you a hint. Here's my hint. This point and this point and this point have to be on the same line. And this piece must equal this piece. So then the graph must be symmetric with respect to the origin. And the relationship is f of negative x equals negative f of x. Extremely important. Is it clear what happened and how we got these two? Yes, yes, we're going to have plenty of examples. Just let me go back and analyze these, and I'll come back. What type of function is this? Odd, even, or none of the above? Very good. The linear function is an odd function because it's symmetric with respect to? Awesome. Quadratic. Because it's symmetric with respect to absolute value. Square root. Not symmetric. Cube root. Very good. Say it again. It's odd, right? Cubic function. Very good. Rational. Yes, odd. So this is a copy of this. That is a copy of this. Yes, very good. It is odd. A rational function is odd. So let me give an example. Let's say we have f of x equals negative x cubed plus 2x plus 5. We are asked, is this function symmetric? And then we look at transformations. Is this function symmetric? What do I have to determine?
What type of function is this?
No, not in this case.
The f of x, f of negative x, or
The other one,
negative f of x?
you can. You can. Let's start with that. I was expecting f of negative x. Here's why. Here's why. Both of them require to determine f of negative x, no matter what. But you're right. I will have to determine this too. I can start with it. Doesn't matter. Doesn't matter. But this is the key. And this is the second key. And then I make a decision. But you're right. I can start with that. Good. So let's find f of negative x. F of negative x is negative x to the third plus 2 times negative x plus 5. So all we have to do is just find f of negative x. So let's do that. Negative x to the third. Yes, with minus in front. Awesome. 2 times negative x. Awesome. Plus 5. So now I have 3 questions for myself. Here's what I'm asking myself. Does this equal f of x? If it does, I'll say even. Does this equal negative f of x? If it does, I'll say odd. Or none of the above. There is only one yes. Only one answer. One answer can have yes. The other 2 have to be no. So let's compare. Is this identical with this? No. So then the function is not even. Now, I do have to determine, as Paul said, find negative f of x. I have to find it. So when I find negative f of x, all I have to do is multiply both sides by, right. So then this will become negative f of x equals x to the third minus 2x minus 5. At this step, I compare this to this. Are they identical? No. Since they are not identical, I'll cross out the odd as well. So what do you conclude about this function? Is this function symmetric or not? Not symmetric. It's not odd, it's not even. That's the procedure. Okay, finally we can start transformations. Transformations mean nothing if we do not know or remember the graphs of those 7 functions. So all these transformations are based on those 7 graphs. And later on, we'll add exponential, we are going to add logarithmic functions, trig functions, and so on and so forth in this course. So for now, we only have 7 functions to play with. So transformations. They are of 3 types, major types. Shifts, vertical, horizontal, reflections, with respect to the x-axis or the y-axis. So this is type 1, type 2, type 1, type 2. And the last one is a combination of stretching and shrinking. I can't find a name for both, so I'll say stretching or shrinking. That's a G. Stretching, shrinking. Type 1, vertical. Type 2, horizontal. That's all. Once we understand transformations, we will have a totally different understanding of functions. And we will be able to build functions. If I say to you, use x squared, or the quadratic function, and shift the graph up 2, down 3, left 3, stretch it by a factor of this, or shrinking by a factor of that, you will be able to create the function. Okay? So let's start with shifts. These 2 are the easiest. Stretching and shrinking vertically, still straightforward. This is the only one that is kind of opposite of what you would expect. Everything else, I think you're going to find it straightforward. This one will be We'll see when we get to it, but I'm pretty sure that you will say, this is not what I would expect. And rightfully so. Okay. So let's start with shifts. I'm going to look at function f of x equals. So I'm going to start with horizontal. Horizontal shifts. Let's say I'm going to call it f1, x plus 4 squared. And I'm going to call it f2, x minus 3, everything squared. I'm going to ask you, which function did I use to create these two functions? Which of those 7 functions I used here? Which one?
Quadratic.
Right. So then the base, sometimes I like to call the simplest possible function the base function. I'm calling it the base function. You don't have to call it the way you like. I'm fine. So when I graph the base function, x squared, obviously I'm changing what? I'm changing x into x plus 4, or I'm changing x into x minus 3. Every time I make a change in x, the graph goes either left or right. If I make a change in y, it goes up or down. Okay, now the question is, where will this function go? And thinking, say it again.
To the left.
Right, y. Y will go to the left.
Negative 4.
Plus 4 will be 0. Awesome, perfect. Thank you. 1, 2, 3, 4. So this will be the graph of x plus 4 squared. Perfect. So then where will the x minus 3 be?
Can you repeat that while it goes left?
I'm sorry?
Can you repeat why it goes left?
Oh, because when I shift from 0, 0, how do I get the vertex? Only if this moves to negative 4. Negative 4 plus 4 will be 0. And where will this move? To the right 3, exactly. So this is the graph of x minus 3 squared. When I set this equal to 0, I get the x-intercept as being negative 4. When I set this equal to 0, I get the x-intercept at 3. Is that better? Okay, very good. Now let's talk about vertical shifts. Okay, so let's say f1 again, the absolute value of x minus 4, and my f2, the absolute value of x plus 5. What was the base function that I used in order to create this function? Very good, indeed. So now, what did I change? As you see, x was not changed. So the absolute value of x is still the absolute value of x and the absolute value of x. The outcome changes now, not the input. The output changes. So where does this graph go in order to create this function? Down 4. Very good. X does not change. Left and right change is a change in x. Up and down change is a change in y. So the original function is this, or the base function is this. But now when I want to graph the absolute value of x minus 4, I have to shift this graph 4 units down and make sure that what I graph is perfectly parallel to the existing base function. So this is the absolute value of x minus 4. How will I graph, or where does the f2 go? Right, of the base function, not this one, right? They're both good. So I'll go 1, 2, 3, 4, 5, and I graph it completely parallel. It's not 100% in my graph. Sorry about that. So the absolute value of x plus 5. So these are horizontal and vertical shifts. I will create now a combo. Here's the combo. F of x equals x plus 1 cubed minus 3. This is a combo. This function does two things sequentially to the same function. I shouldn't say to the same function. The first transformation is on the base function. The second transformation is on the new function I created. To the left one and down 3. Awesome. And it has to be in the order of operations. The exact order you must set it in. So first, the base function is x cubed. Secondly, the transformation that follows is x plus 1 cubed, which is left 1. And 3, x plus 1 cubed minus 3 is not a transformation on the base function. This is a transformation on function number 2. So now this is down 3. I have to show the steps. I will graph the base function. I will shift it 3 to the left, 1 to the left, and 3 down. So here's the base function. I shifted 1 to the left. And now I shift this graph 3 down. 1, 2, 3. That's not a good color. 1, 2, 3. This point moves right here. And the graph will be this. It's not a perfect graph. I don't really know exactly where it crosses the x and y axis. I have not calculated anything. But it's a perfect graph when it comes to picturing the graph of the function in your head and the trend, if you want, or what the function is telling us. Very good. Next step, reflections. Reflections. So I'm going to create f1 as the square root of negative x and f2 as negative the square root of x. Which base function did I use to create these two, f1 and f2? Yes, the base function is f of x equals the square root of x. Awesome. Now, these are two totally different situations. Here, I'm changing x into negative x. So it must be a transformation that happens on x. So from positive x to negative x, what am I doing? Reflecting the graph with respect to the y-axis. Very good. So I graph the square root of x, which is this function. Now you understand that if we don't know how the square root of x looks like, there's no point in discussing transformations. How can I envision anything or imagine transformations if I don't know how to graph the square root of x? Perfect. So now this is the square root of negative x. So when we change x into negative x, what type of transformation we are applying to the base function in this case? Reflection with respect to WRT, with respect to the y-axis. Very good. Perfect. Before I go to the next page, I would like to discuss what we change now for F2. Can anyone look at this and look at this and say, ah, you are not changing x now. You are changing, yes, because the sign is outside. The sign doesn't touch x. So what am I changing is I'm changing y. So when I change positive y into negative y, what am I doing to the graph? Or negative y into positive y, what am I doing to this graph? Exactly. Reflection with respect to the x-axis. So here's now the graph of the square root of x again. This is it. And the graph of negative the square root of x is this. I multiplied all y values. It's outside. I'm multiplying all y values by -1. So this is reflection with respect to the x-axis. Are we okay so far? Awesome. So now the last type, stretching and shrinking. Let's look at the vertical one, and then the horizontal one. Okay, I'm back to my F1 of x, F1 of x, 2x squared, and F2 of x, 1/2 x squared. Which function did I use as the base function to create these two new functions? Quadratic, very good. So the base is y equals x squared. Very good. I'm going to graph the base function. So here's my base function, but this time I'm going to, because I want to illustrate what I'm doing, I'm going to choose some points. So 0, 0, 1, 1, 2, 4, right? Through the function. 2, 4, -1, 1, -2, 4. Agreed? These are the points for x squared. Okay, perfect. So let me graph it. So 2, 4, 1, 1, -1, 1, -2, 4. Very good. So now, first of all, let's identify what type of transformation it is. Is it on x or is it on y? So we have to compare x squared to 2x squared. And we have to say it's a transformation on x or is a transformation on y. Yes. Why is it on y?
It's outside.
First of all, it's outside, and x squared does not change. There is just a number outside that is not 1. So this all y values of x squared, they're multiplied by 1. These all values for x squared are multiplied by 2. So it's a transformation on y. Good. So now please give me a couple of points. We're not going to do this again, just to illustrate the first time. Give me a couple of points that will be part of this function.
Instead of 1, 2 would be, or instead of 1, 1, it would be 1, 2.
Exactly. Instead of
2, 4,
yes,
2, 8.
yes. So bear with me and say that this is 8. So obviously, this must be 2x squared. So what am I doing to the graph? Vertical, vertical, stretching. By a factor of, so this is a vertical stretching by a factor of 2. Okay, can anyone give us the idea for F2? What will that do to the original or base graph? Yes, vertically. So now, instead of 1, 1, where would the point be?
1.5.
Yes. Instead of 1, 4, where would the point be?
G.
It will be a 2, comma?
Comma 2.
Exactly. And so on and so forth. I'm exaggerating on that side. Sorry about that. Let me correct it. So, what do you think this is? It is still vertical, but what? Not stretching, but shrinking. By a factor of 1/2. Very good. By a factor of 1/2. So this, the vertical shrinking, by, oops, I already went to the next word, by a factor of 1/2. Good. Last. Yes.
Does this work with only even?
No.
No, both.
Anything.
Okay.
Any function, any base function. Very good. Let me give a combo now before we look at the last one. Let's say f of x equals 2, the square root of x plus 1 minus 3. What is the base function used to create this function? Good. What is the first transformation in order of operations? Awesome. Which means? 1. Awesome. Next. In order of operations. Very good. 2 times the square root of x plus 1. What will this do? Very good. By a factor of? So vertical stretching. And the last one. 2 the square root of x plus 1 minus 3 is a transformation on number 3. No longer on the square root of x. So this is on this, this is on this, this is on this. Where does this graph go when I want to graph this one? Down 3. Very good. Awesome. So let's graph this. That's why I have 24 colors. Are you proud of me? I'm kidding, I'm kidding. Okay, so here's the square root of x. You told me to shift it 1 to the left. I am going to do that. Then you told me to stretch this this graph by a factor of 2. I'm going to do just that. And then I'm going to shift this graph 3 units down. Is this a perfect graph? No way. I don't have the x and y intercepts. I don't know where it crosses. But it's a perfect picture for me and for you about the trend of the graph. So if you have, for example, a study and you get information, let's say blood pressure or for 100,000 patients, and you plot something like this. Let's say I plot this. What kind of function will you look at? Right? So you only have to find where it shifts to the left and where it goes up. But you know the type of graph that you are looking at. What if I have something like this? Let's say I plot my points and I get something like this. Which kind of function will I? Cubic function. What if I graph and I see something like this? What kind of function will I think of? Right. I don't know where it goes to the left. I don't know how far it goes down. I have to create a function that has a square root in it. Okay? So this is a very powerful tool to look at. Good. Last one. Before I present the horizontal stretching and shrinking of the graph, let's take a look at this. Let's say I have f of x, which is x cubed, and I would like to determine two functions using x cubed. I'm going to call it f1 of 2x, and I'm going to call it f2 as of 1/3 x. What would you write? How will you determine these two functions? Awesome. That's all I need you to say. And I'll come back to it in a minute. And what about the other one? Right. That's very clear because we know how to, when we look at the function, we know what it means. Right? Okay. It says cube the argument. If the argument is 2x, I have to cube it. If the argument is 1/3 x, I have to cube that. Good. And now let's finally simplify this. Without parentheses, what would you tell me to write? Obviously, you will say, awesome. And obviously, you will say, 1 over, very good, very good. Now, forget about this, and forget about this for a moment, and tell me if I just say to you, how would you graph 8x cubed? So I'm going to mimic x cubed. This is x cubed. And I would like you to tell me, how will I graph 8x cubed? Will I graph it like this? Or will I graph it like this? Right. It's a vertical stretching, correct? But look what I did. I replaced the original x by twice x. Shouldn't this be this?
Because your outcome is twice. Oh, wait. Yeah.
So it's against what we would have expected. That's my point. It is correct. Everything we said is correct. But when you look at 2x, wouldn't you say, oh, this must be horizontal stretching? It's not. It's the opposite. It's a horizontal shrinking of the graph. So now let's look at this one. How will you graph this? Will you graph it like this or like this? Like this, right? So it's a horizontal stretching of the graph. But look what we did to x. We didn't stretch x. Exactly. So when we change x into twice x, it's a horizontal shrinking of the graph. Always think in these terms. When we change x into 1/3 x, it's a horizontal stretching of the graph. This is the only one that you probably would not expect this to happen, right? So, this will come into play a lot in Trig. But I can't graph a Trig function right now for you because we haven't gotten there. So, let's graph 8x cubed, or f1 of 2x. So when I graph x cubed, I get this. When I graph f of twice x, I get this. This is f of twice x, which is horizontal. Although you can say, but wait a minute, it's also vertical stretching. I agree. But we are talking about horizontal shifts, horizontal stretching and shrinking now. It's a horizontal shrinking of the graph.
So it's always going to be two transformations at the same time.
You can look at it from two different angles, but it's only one transformation. This function is only one transformation right now.
Well, I'm saying it, even though you're saying it's a horizontal shrinking, it's also. Yes, but you cannot say both at the same time. Okay, but you're not going to ask me for these both.
No. I will not do that to you, promise. Okay, and the other one, I'm exaggerating. So f of 1/3 x is a horizontal shrinking. I'm sorry, stretching of the graph. Okay. Any questions? Any questions?